In all of the previous videos, when we were collecting data and trying to represent the data and summarize the data, we'd ask the individual one question, what is your height? We write that down, and we have a whole bunch of numbers, and that is our data set. At this point, we're going to now move on and say, instead of asking that person one question, let's ask them two questions. Let's say, what is your height and your weight? Or what is your age and your weight? Or how much money do you make and what is your age? We're going to ask them two questions, so each individual is going to have two pieces of data. And what we're going to do is we're going to graph those, one with the x and one with the y. Now, we have to decide one of them to be the response variable and one be the explanatory variable. So response versus explanatory variable. Now, the thing is, there isn't necessarily a right answer to this. I mean, does the person's age determine the amount of money that they make in a year? Well, certainly there's some sort of effect there between that. Generally, people, as you know, if they're in their 20s, they're going to earn less than someone in their 40s and so on. But is it just because they got older that they're making more money, or is there something more to it, right? So don't get too tied up into thinking that one of these is actually directly causing the other one, and that's why one is the response and one is the explanatory. That's just what we're going to call them here. So we have to pick one of the data values to be on our x-axis, one of the data values to be on our y-axis, and then we're just going to graph all these points. And maybe it looks something like this. And this is called a scatter diagram. So again, scatter diagram is just take all your pairs of data, your x's and y's for each person that you had, mark it on a graph. That is your scatter diagram. What we're going to then be doing now is we're going to say, looking at the scatter diagram, what can we tell? Is there any kind of pattern there? Can we do any calculations based on this pattern? Can we make any predictions? And so on. That's where we're heading at this point. So to kind of do some more details on that, first off, we have the idea of association and a very similar idea of correlation. And they come in positive and negative variations here. So what exactly do we mean by this? So positive association means generally as you increase the x value for whichever one you chose to be on the x-axis, the y value will also increase. Now, I do want to very much underline generally here. It doesn't mean that every single time if you increase your x value, the y value has to get higher. And that kind of goes along with how nothing in this world works out perfectly. So sometimes it's going to go down. Sometimes you have weird data there, right? You might have someone that is taller but weighs less. You might have someone that is older but makes less money. So it's not always going to be guaranteed to be the case, but generally, taller people are going to weigh more. Generally, people that are older are going to earn more, at least to a certain point. So that's what we mean by a positive association. Negative is the exact flip here. So negative association means generally as x increases, y decreases. So as you get bigger values on your x variable, you're going to get smaller values on your y variable. Now, we call it association when it's just any type of relationship that's kind of going up or going down. But if you want to restrict yourself to things that are close to a line going up or close to a line going down, that's the correlation here. So correlation is when the association is roughly linear. giving a couple of quick graphs here. So this something would be a positive association. It would also be a positive correlation. The data points don't perfectly line up in a line, but they are pretty close there. So because it's close to a line, we say it's correlation, not just association, but association can be anything that's related. On the other hand, if we draw something that looks like this, then it's still generally going up as you go left to right, but it's not really a straight line. It's curved there. It's almost maybe like an exponential graph. And so that one would be an association that is not a correlation. So correlation is limited to things that are going to be like straight lines or close to straight lines. Association is the more general term. Now, who's going to decide whether something is close enough to a straight line? Like what if on the correlation up here, what if I have a data point that's kind of far off? Well, most of them are a straight line. Is that going to be okay? What if I have another one that's kind of off? So the question is exactly how close to a straight line does it have to be? Well, we have a way to, in a sense, measure that. It's called the correlation coefficient, also known as the Pearson correlation coefficient, named to the person who came up with it. I'm going to go ahead and give you the formula now, but really don't even bother with memorizing this or don't even think about this formula. It's an awful formula here. Let me just write this whole thing down, and then I'll talk a little about what's going on in here. And you're probably getting scared already with how much stuff is going on in this formula. But I will just tell you before I even finish writing the formula down, yes, your calculator will do this for you. So you don't have to worry about doing this awful thing yourself. Okay, so this mess, right, it's a gigantic fraction with a whole bunch of stuff on top, a whole bunch of stuff on the bottom. The n is your sample size. The xi and yi, those are your data points, right? You have an x and a y for each individual there. So it's saying you start out by multiplying your x and y together, add up all those answers, multiply it by the sample size, then minus, and then each of those says you add up all the x's separately, add up all the y's separately, multiply those two answers, and then you do the subtraction. On the bottom, you have these square roots of n times sum squared. So it's a gigantic mess. As I said, we are going to be able to do this in our calculator without doing all the hard work ourselves. You're just going to put in the x's and y's, hit a couple buttons, and it will tell you what your r is. You don't have to worry about that. Now, this r is going to have certain important properties for us. One of the first properties is that the value of r is always between -1 and +1. So this is one of the things I would always point out back, when I was teaching this class a long time ago. We did have to do this by hand. Our calculators wouldn't do it for us. And in those classes, I would always warn my students that, hey, if you do your calculation and you get like an r of 5, that means you did something wrong. It is not possible to get an r of 5. It's always going to be something between -1 and 1. And then what I can do is we can say the following here is the closer the absolute value of r is to 1, the better the linear approximation. So if you have an r value that's like 0.9, and it could also be -0.9, something that's close to 1 in absolute value, that means it's going to be closer to a straight line. Whereas if you have an r value that's close to 0, so if r is close to 0, then data is not close to a straight line. Let me write that better here. Now, it doesn't mean that there is no relationship in the data. It just means that the relationship is not going to be something close to a straight line. So there may be no relationship at all, or it may be like a parabola relationship or something more complicated. But if your r value is close to 0, it's not going to be a line. And I will just say that in our class, we are only interested in the line version of this. If you want to learn about the more complicated versions, you can go ahead and take more statistics classes. But for us, we're just interested in the line value here. Is it going to be close to 1 or close to 0? With that said, what does close really mean here? How small does it have to be? So as a rule of thumb, and again, this is not something that everyone would agree on, but if R is bigger than like 0.7, let's say, then we will consider the variables linearly correlated. Not very strongly, but at least there's some sort of kind of linear relationship there if your R is at least 0.7. And the larger you get, say 0.9, 0.95, that's going to get better and better and better. And you can only get R equals exactly 1 when the data is perfectly on a straight line. So keep that up there. Now, so what we're going to do is we're going to learn how to calculate R. We're going to see examples of that in the calculator. And then we're going to say, well, okay, if it is close to a line, how am I actually going to find that line and what the equation line is? But that'll be for a different video. There's the last thing I want to talk about, though, is that doing all of this, we calculate correlation. We can just say that these two variables are correlated, either positively or negatively correlated. Right? If our R is 0.8, they're positively correlated. If R is negative 0.9, they're negatively correlated. But I want to point out here that correlation, see it says versus causation, so correlation does not guarantee causation. So just because you have two variables that are correlated, that have a nice relationship between them, does not mean that one of them causes the other one. And this is something that even professionals in news programs mess up on here all the time. The people will do a study, they'll show these two things are correlated, and then they'll try to claim that one of them is causing the other one. And that is not true at all. It's a very difficult claim to make, to say that one thing causes something else. And a simple correlation calculation is not going to do that. And if you want to, I'd recommend, Googling, bad correlations, or there's this website called Spurious Correlations. And it says things like the number of movies starring Nicolas Cage in a year versus the number of teen suicides in a given year are correlated. So what that means is that the years where Nicolas Cage had more movies ended up having more teen suicides on average. But I don't think his movies are the ones causing that, right? So there's a lot of these weird relationships you can find out there. And like I said, some of them are pretty funny and they just make no sense. And I just want to point out that just because they're correlated does not mean one's causing the other one. In fact, they might not have any causal relationship whatsoever. So just understand that correlation absolutely does not mean causation. Keep those two ideas separate in your head.